So as we have discussed in the previous lecture, that in this lecture we are going to discuss regarding Versta's approximation theorem. Before going to the Versta's approximation theorem, let us understand what is this theorem is. And we will not prove this theorem in this lecture, we will prove this theorem in the next lecture. So first we'll understand what is this theorem is, and then we'll build up some of the things which we require to prove this Versta's approximation theorem. So what is this theorem tells you that if you have a function, let f be a function from AB to R, be a continuous function. F is a continuous. Then given epsilon greater than 0, there exists a real polynomial functions Pn, or I can say P, such that f of x minus p of x is less than epsilon for all x belongs to AB. In particular, there is a sequence of polynomials Pn, so that, or I can say there exists a sequence Pn of polynomial such that Pn will converge to f uniformly on AB. So this is the Versta's approximation theorem. It says that means if you have any given continuous function, any continuous function is there, then there will be a sequence of polynomials exist such that the Pn, this sequence of polynomial, will converge to the function f pointwise, uniformly. Now let us understand, as I have discussed in the previous lecture, a meaning of the Versta's approximation theorem. So as I told you that in the previous lecture, that if you want to plot a graph of a function y equal to f of x, any graph of the function, let's say y equal to sin x, then what we will do, we will plot some points x and y, and corresponding we will find out what are the values. So we will fix the points of x. Let's say it is 0, pi by 4, pi by 2, 3 pi by 4, and pi. And then correspondingly we will find the value of y. And sine 0 we know it is 0, sine pi by 4 it is 1 by root 2, pi by 2 will give you 1, 3 pi by 4 is again 1 by root 2, and pi will give you 0. And as per the things we will plot, this is on the graph. That means if you have, this is a 0 function, 0 point, this will be your pi by 4, this is pi by 2, this is 3 pi by 4, and pi. And then you will plot 0, 0 point, then it is pi by 4, comma 1 by 2. Suppose this is your 1, then 1 by root 2 maybe somewhere here, 1 will be here, then again 1 by root 2 will be here, and 0 is there. And then what we will do is we'll join this by one continuous curve. Actually, that is a continuous function. That is this function y equal to sin x. The question is why there is no such graph is there. In between there is, it may be possible this is the graph is there in between or joining these points, but why it is not, why we can plot or in this manner, that is our sine graph, is whatever the graph you will plot here in between, joining these points, all this graph are continuous. So this Versta's approximation theorem says that there is one sequence of polynomial. That means this all the polynomials which are passing through those points. This we have with the black color. And if I can draw all the graph which are passing through these points, whatever the graph, whatever the polynomials you can plot, all of them will converge to this red graph which we have plotted earlier of sine graph. All these green graphs, a sequence of green graph, will converge to this graph, that is sine x. So that is exactly the Versta's approximation theorem is this. This theorem was established in 18th century, as I told you earlier. And in 1923 or 1921, the Versta's approximation theorem is proved by S and Bernstein. And he has proved this theorem using the Bernstein polynomials. So in this lecture, actually, we will discuss regarding this Bernstein polynomials. The Bernstein polynomials are defined. So why this is known as a Bernstein polynomial? Because the Bernstein was the first mathematician. He has proved the approximation theorem using this polynomial. The Bernstein polynomial is defined for the function. Let f be a function defined on closed interval 0, 1. So f be a function. And the Bernstein polynomial for this function f associated with f, I can say. The Bernstein polynomial Bn associated with a given f is defined by this way: Bn of x. I should say Bn fx, because it is f is dependent. Sometimes it's just denoted as Bnx, or it is also having the notation is Bn f at x. These are all the notations. In different books you can find different notations. That is equal to summation k running from 0 to n. So it is actually a polynomial. Okay, so it is degree is n. So it is, I can say the Bernstein polynomial is of degree n. Is x power k 1 minus x power n minus k nck into f of k by n. And what is the reason for this definition? It actually leads to in the probability theory. So if you can and the proof of Versta's theorem is also using the Bernstein polynomial is originated in the probability theory. So how? Let us see this. So we have a based coin. Suppose we have a based coin. Turn a head with the probability is between 0 and 1. Let's say is a probability of turning head is t, which is between 0 and 1. Now what has happened? A player lost the coin n times. Suppose he lost the coin n times, then the probability of getting head k times, let me write what I'm saying. Okay, so if a player toss the coin n times, the probability of getting the head k times is given by nck t power k 1 minus t power n minus k. Now you can just see that, and it is actually a binomial distribution which we have seen. Now here a k by f of k by n is there. Now what is this f? It is actually a payoff, a sign, a prize. So if the player will get f of k by n rupees if we get exactly k head out of n toss. Okay, so what I'm saying, the player will get f of k by n rupees if he get exactly k head out of n toss. So out of n tosses he will get exactly k head, and this much rupees he has to assign. So that means the player will get out of the game of n toss, so the expected value en, the expected value en, the player like to get out of the n toss is summation k running from 0 to n f of k by n nck t power k 1 minus t power n minus k. And this is nothing but the nth Bernstein polynomial, or I can say it is a Bernstein polynomial of n degree of f. This is the average, or I can say mean value of the game of n tosses. This is what? It is the average or a mean value of the game of n tosses. And the expected that the n is very large. If the n is very large, the head will turn approximately n into t times. That is the expected value of the binomial distribution. That is n into t times the head will turns up. And thus, this implies the price which we get, it is f of t into n upon n, which is f of t. So what is exactly what is happening? When n is very large, then this en and f will be near to each other. So what we expect that this en of t is minus f of t will tends to 0 as n tends to infinity for large n. And this we will prove in the next lecture. So this is the idea how this proof of this Versta's approximation theory is leads down in approximation. Leads down in the probability theory. Here Our objective is to discuss some of the moments of the Bunsen polynomial. And this moments is for zeroth moment, first moment, and the second moment. And we will discuss also central moment for this function or this polynomial, Bernstein polynomial. So let us discuss that here. So as I have defined Bn of fx, or I can say Bnf at x, which is equal to summation k running from 0 to n nc k x power k 1 minus x power k f of k by n. Let us consider this function f of x is equal to 1 for all x which is in Roche interval 0 1. So that means this is fn at 1 at x. This 1 is a function. So as per this argument or as per this expression, we'll say it is summation nck x power k 1 minus x power n minus k, and this f of k by n, since f is a 1 for all x belongs to 0 and 1, we will have 1 here. And according to the binomial expansion, this is not k running from 0 to n, this is k running from 0 to n. So as per the binomial expansion, this is nothing but the x plus 1 minus x power n. So we know that the binomial expansion of a plus b power n will be summation k running from 0 to n nck nck a power k b power n minus k. So as per this, if this is your a, that is x is your a, and b is 1 minus x, then we will have this. And so this will gives you 1 raised to n, and so it is 1. So I can say the zeroth moment of this Bernstein polynomial is 1. So this is equal to 1. Now let us calculate Bn, or let consider f of x is x for all x belongs to 0 1. That means it is the identity map fnx fx at 1. So for that, let us see this. Bn f at x, we know it is summation k running from 0 to n nck x power k 1 minus x power n minus k f of k by n. Now f of x is x, so it is Bn x at x. So it is a function x, which I can write down summation k running from 0 to n nck x power k 1 minus x power n minus k into k by n, because f of x is equal to x. So f of k by n will give you k by n. Now let us see what is this k by n into nck. K by n into nck, as per this, which is k by n into n factorial upon k factorial into n minus k factorial. So 1k is get cancelled out. This is k minus 1 factorial. And 1n is also cancelled. So this will be n minus 1 factorial. So what we got? We got n minus 1 factorial upon k minus 1 factorial n minus k factorial. This I can rewrite as n minus 1 factorial upon k minus 1 factorial into n minus 1 minus k minus 1 factorial. So what exactly I did it, I have subtracted 1 and minus 1 in this bracket. And we can observe that nck is n factorial upon k factorial into n minus k factorial. This is n minus 1 c k minus 1. So k into k by n into nck is this. So hence this is we get summation k running from. Now nck n minus 1 c k minus 1 is start. It will not define for negative numbers, and so it will start with k running from 1 to n, and that is equal to bn x at x, that is n minus 1 k minus 1 x power k 1 minus n power n minus k. Now to adjust this, we'll replace k minus 1 by k. So instead of k minus 1, we'll replace k here. So what we get? We will get a j is running from, or I can say k minus 1 is equal to j if I replace this. So instead of starting k is running from 1, now j will start with 0 and n is start with n, so it will start with n minus 1. N minus 1 j, instead of k minus 1 is j, x power j plus 1, 1 minus x power n minus k minus, n minus j plus 1. This quantity I may rewrite as summation j running from 0 to n minus 1, n minus 1 j. The 1x I may write down outside. This is x power j, and this quantity 1 minus x I may write as n minus 1 minus j. Now this is again, you will have the expression is same as summation k running from 0 to n nck a power k b power n minus k, which is a plus b power n. So instead of n we have n minus 1 here, and instead of x we have, a we have x here, and instead of b we have 1 minus x here. So hence this will gives you x into x plus 1 minus x whole power n minus 1. So x will get cancelled. Finally we'll have 1 power n minus 1, so it will have x. So ultimately what we got, it is bn x at x will be x, or I can say bn px will be x. So this f is a function which is f of t equal to t. This is the things we got. So secondly, this is known as a first moment of the Bernstein polynomial. The second moment, for the calculating the second moment, you required your function fn, or sorry, f of t will be t square for every t belongs to 0 to 1. So this is your function t square. Now let us calculate dn at t square x, which is summation k running from 0 to n, nck x power k 1 minus x power n minus k into f of k by n. But f is this function t square, so it is k by n whole square. Now we have to simplify what is this k by n whole square. So let us see now, k by n square into nck. So that I can write down k by n into k by n into nck. And k by n into nck, we already have established quantity here, that is n minus 1 c k minus 1. So this quantity we can write down k by n into n minus 1 k minus 1 for k greater than or equal to 1. Okay, for all k which are greater than or equal to 1, we can write this. Again, what will be this quantity? So for that, we'll adjust something here. So here we have given k by n, which I can write down k minus 1 plus 1 upon n into n minus 1 k minus 1 is there. Actually what I am trying to do is making the same expression as we have here, that is which we have done k by n nck. So what is exactly what we are doing is this. So actually what we have is k by n, nck is n minus 1 k minus 1. So ultimately what I want to do is I want to express this k minus 1. So exactly I am trying to get this expression. Instead of k we have k minus 1, instead of n we have n minus 1 here. So I am trying to get this expression over there. Since we have already adjusted this k minus 1, now we need to adjust this n. So I can write down this is as k minus 1 upon n minus 1 into n minus 1 upon n. So n minus 1 I have divided and subtracted, plus 1 upon n is already there. N minus 1 k minus 1 is there. Now this, if you multiply these two brackets, then we will have it is k minus 1 upon n minus 1 n minus 1 c k minus 1 into this n minus 1 upon n is already there, so that is 1 minus 1 by n, and plus 1 by n into n minus 1 k minus 1 is there. And this expression, as per this, we can write it is n minus 2 k minus 2. So this is, we can write 1 minus 1 by n minus 2 k minus 2 plus 1 by n minus 1 k minus 1, which is true for all k greater than or equal to 2, because otherwise this expression n minus 2 c k minus 2 will not define. And what is this? It is k by n square nck. This is the expression we have. Now we'll do this. So I'm putting this value here. That is k by n square into nck. So as per that, bn t square x is summation k running from 0 to n ck into k by n whole square x power n 1 minus x power n minus k is already have. Now the value of this quantity we have obtained it here, which we can substitute. So we can have a two summation, but we'll write in two steps. The first one is this, but now it is not start with 0 because it has to be start with k greater than 2. So it will start with 2. Here in the first it is 1 minus 1 by n minus 2 k minus 2 x power k 1 minus x power n minus k. This is the first summation plus the other quantity is 1 by n minus k, n minus 1 c, k minus 1. That is another quantity. So that is another summation we have. So that we can write down 1 by n. Now k running from 1 to n because it will start with that n minus 1, k minus 1, x power k, 1 minus x power n minus k. Now this is independent of n, so I can take out from this summation. And here in this first summation, I am replacing k minus 2 by j. So that is j running from 0 to n minus 2. N minus 2j x power j plus 2, 1 minus x n minus j minus 2. And the second summation I am going to replace k minus 2 replaced by, k minus 1 is replaced by j. So it is 1 by n summation k running from, j running from 0 to n minus 1, n minus 1 j x power j plus 1, 1 minus x power n minus j minus 1. Now as per this, what we got, it is from the first summation x square is common out. So it is 1 minus 1 by n x square into the rest of the quantity is exactly x plus 1 minus x power n minus 2, which we already discussed earlier why this will come. And that is 1 by n. The second summation will 1 by n. X is common out from this. And the rest quantity is x plus 1 minus x power n minus 1. Hence, the left quantity is 1 minus 1 by n x square plus 1 by n x. So this is the second moment for the Bernstein polynomial. Now we have to establish what is the central moments. And one should note that this Bernstein polynomial is a linear operator. What do you mean by linear operator? Let me define a linear operator. Suppose Ln be a map from one nonlinear space to another nonlinear space. That's why it is an operator. So it is mapping from x to x, which is linear. If you can say that f plus g is equal to ln of f plus ln of g, and ln of alpha f is alpha times ln of f. So this is known as a linear operator. Probably you have learned that concept in your linear algebra course. Here this Bn, which we have, it is an linear operator. How we can say that? as in this manner: Bn of f plus g at t, which we can say summation n running from, summation k running from 0 to n, nck x power k 1 minus x power n minus k. Instead of f we have f plus g. So as per the pointwise pointwise addition, f plus g at x will be fx plus gx, we can write. So, and this summation I can give to both of them. So it is summation nck x power k 1 minus x power n minus k f of x plus summation k running from 0 to n. You can write all sort of things: nck x power k 1 minus x power n minus k into g of x. So this is what? This is b and f at x, and this is b and g at x. Here it is x, not t, if I can write x here. So this is equal to this. So that means the addition is preserved, and same way one can prove that the scalar multiplication is also preserved. So ultimately what we have proved is this Bn of f, or Bn is the linear operator on C01 to C01. Now the central moment, which I can define as t minus x. What is this f of t here? It is t minus x. For every t belongs to closed interval in 0, 1 with fixed x. So this is my function t minus x. So I can say it is t function and the constant function x. So as per that discussion which we have discussed just now, it is a linear operator. We can write down this is Bn of tx minus Bn of x. This is a constant, so that I can write down Bn of tx minus x Bn 1x. Bn of x already calculated earlier, that is for the first moment which we have derived, and we got it is x, which we have here. Bn of x is x. So that is x minus b1 of x, b is also 1, so it is x into 1, so which is gives you 0. So the first central moment of this Bernstein polynomial is 0. Let us calculate the second central moment, that is t minus x square x, which I can write down Bn of t square minus 2tx plus x square x. And then using that linear operator things, which we can write down Bn t square x minus 2x is a constant according to t. Bn of tx and x square Bn of 1x. Bn of t square, that is the second moment which we have calculated, is this, that is 1 minus 1 by n x square plus 1 by n x, which I can write down here. This is equal to 1 minus 1 by n x square plus 1 by n x minus 2x. Bn of t is x, which we already calculated, plus x square into 1. Bn of 1 is 1. So hence what we achieve is 1 minus 1 by n. This is x square, this is x square, and this is x square. So it is minus 2 plus 1 x square plus 1 by nx. So you can just see that this will cancel out. So only quantity is left. is x minus x square upon n, which I can say x into 1 minus x upon n. Okay. So what we have achieved here is Bn of t minus x square comma x is x into 1 minus x upon n. Let me write Bn of t minus x comma x is x into 1 minus x upon n. We'll use this one. And many a times in examination, this expression have been asked. That is, what is this Bn of t minus x square? Let me write that. Summation k running from 0 to n, nck, x power k, 1 minus x power n minus k. And instead of the function f of t, we have t minus x, but that is f of k by n. So instead of t, we have k by n. So this is k by n minus x whole square is equal to x into 1 minus x by n. And if I take the LCM as n square here, then this is the expression we can write down summation k running from 0 to n, nck, x power k, 1 minus x power n minus k, k minus nx whole square, and divided by n square is there. But this summation is independent of n. So that's why I'm just multiplying n square both sides. We'll have n square into x 1 minus x upon n. So finally we'll have nx 1 minus x. And for all values which are between 0 and 1, and in between 0 and 1, this function x into 1 minus x has the maximum value is 1 by 4, which I can give you as an exercise, that if fx is equal to x into 1 minus x, if your x is between 0 and 1, then prove that f of x is less than or equal to 1 by 4 for all x which is in 0, 1. It's very straightforward proof. But I will give you one of the shortest proof. But one can prove this is by easily by a calculation or a calculus, by taking the first derivative and equal to 0 and then find out double derivative, all the stationary points, and the double derivative, if it is negative, it will give you maximum. At that point, we'll have a maximum of that value. But here I'm giving you one of the shortest one, that is 2x minus 1 whole square. We know it is always greater than or equal to 0. So 4x square minus 4x plus 1 is greater than or equal to 0. So hence we can say that 4x square minus 4x is greater than or equal to minus 1. So it will give you 4x minus 4x square is less than or equal to 1. So which will give you, if I can take common 4x, that is 1 minus x is less than or equal to 1. And x into 1 minus x is less than or equal to 1 by 4, which I have told you to prove. So ultimately what we have achieved is this quantity is less than or equal to n by 4 for all x which is in between this. So finally what we have achieved, this quantity, that is summation of this one, is less than or equal to n by 4, and this things we will use to prove the Versta's approximation here. So here in this lecture I have defined what is the Bernstein polynomial, what is the first moment, what is second moment. Let me write and conclude as a corollary, also lemma. What we have discussed is this, is Bn of 1 x is 1, Bn of tx is x, Bn of t square x, which we have obtained, is 1 minus 1 by n, x plus 1 by n. Then we have discussed another lemma which based on the central moment, that is Bn of t minus x at x is 0 and Bn of t minus x square x is x into 1 minus x upon n, which we have proved that it is less than or equal to 1 by 4n. Okay, so this is the quantity which we have obtained in this lecture. We'll prove, means we will use this things to prove Versta's approximation theorem into the next lecture. Okay, if you have any doubt, you can ask.